This is the 8th video in our 10-part series on quantum computing. I'm Professor Priya, and today we'll explore one of the biggest challenges in quantum computing, noise and how to correct it.
Professor, I've heard quantum computers are really fragile. What exactly goes wrong with them?
Great question, Sneha. Quantum systems are incredibly fragile. Even tiny vibrations, temperature changes, or electromagnetic fields can destroy the delicate quantum states we need for computation. There are three main types of quantum errors. Bit flip errors, change 0 to 1 or vice versa. Phase flip errors change the quantum phase. And general errors are combinations of both.
This sounds like regular computer errors. Can't we just make copies of our quantum bits to back them up?
Excellent thinking, Arjun. But here's the problem. Quantum mechanics forbids perfect copying of unknown quantum states. This is called the no-cloning theorem. Also, measuring a qubit destroys its quantum properties. Peter Shor, yes, the same Shor from Shor's algorithm, invented the first quantum error correction code. It encodes one logical qubit into 9 physical qubits using clever entanglement.
9 qubits does seem like a lot. How exactly does this encoding work? Can you show us the process?
Here's the clever part. Shor's code first protects against bit flip errors by encoding into 3 qubits. Then it protects against phase flip errors by encoding each of those into 3 more qubits. 9 total! Andrew Steane developed a more efficient code using only 7 qubits. It's based on classical Hamming codes, but extended to handle quantum errors. More efficient than Shor's 9-qubit approach.
Wait, I'm confused. How can we detect errors without measuring the qubits? Won't measuring destroy the quantum information we're trying to protect?
Brilliant question. We use syndrome measurement. We don't measure the data qubits directly. Instead, we use auxiliary qubits called ancillas to extract information about what type of error occurred without disturbing the original data. Here's the amazing result. The threshold theorem proves that if we can keep error rates below about 1%, we can perform arbitrarily long quantum computations by adding more redundancy.
That sounds promising. How close are current quantum computers to achieving this error threshold? Are we there yet?
We're getting close. Companies like Google and IBM have demonstrated error rates approaching the threshold. Google's latest quantum processors show error rates around 0.1% for their best qubits. Very encouraging progress. Let's summarize. Noise and decoherence are the main obstacles to scalable quantum computers. Quantum error correction uses redundancy and entanglement, not copying, to protect information. The threshold theorem proves fault-tolerant quantum computation is theoretically possible.
This has been fascinating, but I'm curious about the actual hardware. How do we physically build these qubits in the real world?
Perfect segue, Arjun. In our next video, we'll explore quantum hardware and discover how different technologies like superconducting circuits, trapped ions, and photons realize qubits physically. See you next time.